Hey guys, Jake here, coming at you with another math lesson today. Gonna go ahead and do another live stream here, going over. I got a few problems prepared for you guys here, but of course, as we go along the way, if you have any questions about the problems I'm doing, or any other questions, any homework problems or something you got going on that you want to ask about, feel free to drop them in the comments in the chat, and I'll do my best to answer any questions you guys have. Of course, if they're on topic, perfect. If not, throw them in there anyway. We'll see what we can do for you. But I got 3 problems prepared for you, so we'll go ahead and get going on those and see how we do. So this is the first problem we have here. We're going to go over this one. Today we're going to go over a few topics which are included in my my free Calculus 1 study guide and in my complete Calculus 1 package. If you want to check those out, there are links to all those things in the description. So just pull that up and go check those out real quick. If you go, you can go get the study guide right away. It'll, put in your email. I'll email it to you. You'll have it, so you can have that pulled up while we go through these problems. If you want to do that, it is free. But let's go ahead and jump into this problem. So first of all, what we're going to do is we're going to find the critical numbers of this function, and we're going to determine if they're a local maximum, local minimum, or a neither. So really, when you're doing this kind of a problem, really the process is going to be pretty similar for any type of problem where you're trying to find the critical numbers and figure out if they're local maxes or mins. Really, all you're going to do is, first of all, you need to find the derivative of the function. So that's always going to be your first step. So to do that, we're just going to take the derivative of this function. There's actually 2 different ways we could find the derivative of this function. We could expand out, FOIL out this x minus 4 squared piece. We could rewrite that as x minus 4 times x minus 4 and FOIL it out. Or we could solve it using the product rule, which is what I'm going to do here in this case. So the product rule, we basically just need to call one of our pieces f. So we'll go ahead and say f is this x to the 4/5 part. And then we need to call our other part g. So we'll call g x minus 4 squared. And then what we need to do is find f prime, which we can find just using the power rule. So do keep in mind, this f of x, this is a little deceiving. This f of x is obviously different from this f of x, or this f right here. This is just kind of using the product rule formula. So kind of consider what I have written in this green color here as like kind of a separate subproblem with different, the f here is not the same as the f up here. But anyway, we can find this just using the power rule. So we'll just take our power, bring it down in front, and then keep our base as x, and then lower our power by 1. So our power is now going to be 4/5 minus 1, which if we're doing 4/5 minus 1, we would need to get a common denominator. So we would need to get it to be in terms of fifths, which means 1 is 5/5. So 4 minus 5 would be -1, and our denominator would stay as fifths. So our new power is going to be -1/5. And then we need to find our g prime over here, which we're going to do using the chain rule. So chain rule says we're going to take the derivative of our outside term. So our inside term is going to be what's in the parentheses here. Our outside term is going to be basically what's outside of the parentheses. So we'll take our power of 2, bring it down in front, just doing the power rule here. And chain rule says we're going to do the derivative of the outside function, which is this 2 here. Leave the inside function alone. So leave x minus 4 as x minus 4. And then lower our power by 1. 2 minus 1 is just 1. Anything to the 1 power is just itself. So we don't even need to write it really. And then by chain rule, we would multiply by the derivative of this inside function. Well, the derivative of x minus 4 is just 1. So by taking the derivative of our inside function, that's also not really going to change our function. So our g prime will just be 2 times x minus 4. And then product rule says that we need to multiply across here. So we're going to do f times g prime, so times 2 times x minus 4, and then plus our f prime times g, so plus 4/5 times x to the -1/5 times x minus 4 all squared. And then this is going to be the derivative of our original function. So this is our f prime of x. So to find critical numbers, what you have to do is find the derivative and then set that equal to 0. So we're going to take this whole thing and we're going to set it equal to 0. Now, what we are going to kind of think about here before I write this next step here of setting it equal to 0, let's think about how we can factor this, because usually when you are finding critical numbers, you take your derivative, set it to 0. It's going to be helpful if you can factor it somehow. So when we're trying to factor this out, what we want to do is look for basically anything that these two kind of chunks here. So if we consider basically this to be one of our terms and then this to be our other term, because everything within each of these terms is being multiplied together. So we have this times this times this. Same thing over here, 4/5 times x to the negative 1/5 times this whole piece here. So what we want to look at is, what do these two terms have in common? Well, they both have x raised up to some power that has 1/5 as the denominator. There's kind of a couple different ways you could think about factoring this out. But let's go ahead and just say that we're going to factor out x to the 4/5. And the reason why we want to just factor out this whole piece here is because really it's not going to matter what you factor out as long as you're factoring out x to some number of fifths power, because what we're going to be able to do is kind of divide each of these terms by whatever we factor out. It's usually going to be easier to pick something you actually have here. So we're either going to want to factor out x to the 4/5 or x to the negative 1/5. You could go either way. I'm just going to kind of go with this one. Then you can see that both of these terms have an x minus 4. So we can factor out x minus 4 as well. And that'll be it. So now we want to think about, if we factor out these two pieces here, what would be left of each of these terms here. So basically, if we take out x to the 4/5, that's just going to be gone. And then if we pull out the x minus 4, that's just going to be gone. So this whole first term, factoring out these two things, is just going to be left with 2. Okay, then over here, we have a 4/5. So we're going to have plus 4/5. The x to the negative 1/5, we basically pulled out an x to the 4/5. So what you want to think about is, what would we have to multiply by x to the 4/5 to get us back to x to the negative 1/5? Well, if you're multiplying two things with the same base, you would add their powers. So in order to get from x to the 4/5, multiply it by x to some other power, we want to get to x to the negative 1/5. So what would you have to add to 4/5 to get to negative 1/5? Well, it would just be minus 1, right? 4/5 minus 1 gives us x to the negative 1/5. Then we still have another x minus 4 term here, because it was x minus 4 squared. Now there's just going to be an x minus 4 term left. So the reason why we wanted to do that is, when we're setting all of this equal to 0 and trying to solve for x, it's easier when you have everything all factored out, because what we can do now is we can create 3 simpler problems out of that, where we can just take each of these factors by itself. So each of these 3 things, if any one of them equals 0, then the product of all 3 of them will be 0, because 0 times anything is also 0. So as a result, what we can do here is we can say these 3 separate problems of x to the 4/5 equals 0, x minus 4 equals 0, and then this whole piece here. So 2 plus 4/5 times 1 over x, because x to the negative 1 is the same as 1 over x, times x minus 4, all equals 0. So this problem here, really we can just do both sides raised up to the 5/4 power to cancel that with that, and we're just going to get x equals 0. For this one here, we would just add 4 to both sides, giving us x equals 4. And then this one's going to be a little more complicated. We're going to want to start kind of moving different terms over to the other side here. So we can subtract 2 from both sides, giving us 4/5 times 1 over x times x minus 4 equals -2. Multiply both sides of the equation by 5 over 4 to cancel with this one. And then what we can do is we can distribute the 1 over x into our parentheses here. So doing that is going to give us 1 over x times x is just 1 minus 4 over x. And then over here, this 2 is going to cancel with that, making it a 2. So we're just going to have minus 5/2. And then we really just have this one x term here. So we want to kind of move the other stuff over. So -4 over x equals -5/2 minus 1 is the same as -5/2 minus 2/2. So that's going to be minus 7/2. And then what we can do here is we can kind of cross multiply. So we'll multiply the denominator of the left side times the numerator of the right side. So that'll be -7x. And then the numerator of the left times the denominator of the right. So that'll be -8. And then we can divide both sides by -7 to get x equals 8 over 7. So we have our 3 critical numbers, x equals 8/7, x equals 4, and x equals 0. So now what we need to do is figure out which ones are local maximums versus local minimums or neither. So to do that, there's 2 different ways we could do it. And it's really up to personal preference of which one you like to do. We could either do the first derivative test or the second derivative test. So to do these, and like I said, both these tests are on my free calculus study guide if you want to go over to Jake's Math Lessons and grab that real quick. So you can see exactly what I'm talking about. But basically for the first derivative test, what you want to do is basically draw out a number line. So we're going to draw out our number line here. And what the kind of main numbers that you want to write on here are whatever your critical numbers are. So we want to put 0, 4, and 8/7 on our number line. So we'll put 0, 8/7. That's just over 1. And then x equals 4 will be over here. So whatever your critical numbers are the points that you put on your number line. And then for the first derivative test, what we want to do is grab numbers in between these different intervals. So in between there and there, in between there and there, and then in between here and here, and then over here, and plug them into the first derivative to see where our function is increasing and decreasing. So it doesn't really matter what number you pick as long as you pick one number from each of the intervals that you create on your number line, where the edges of the interval is your critical numbers. So we'll just want to put some number over here to the left of 0. So let's just say x equals -1. Some number between 0 and 8/7. 8/7 is just over 1. So let's just go ahead and say +1. Some number between 8/7 and 4. Let's just say 2. And then some number greater than 4. Let's just say 5. So basically what we can do is then plug these 4 numbers here into our first derivative. So into this function here, which I factored out to give us this right here. Really doesn't matter which one you plug it into, but what we're trying to figure out is our first derivative greater than 0 or less than 0 for each of these 4 numbers? If it's greater than 0, that tells us our function is increasing in that interval. If it's less than 0, that tells us our function is decreasing in that interval. So we can plug in x equals -1 into this whole function here. And if we do that, what we are going to find is we would get -1 to the 4/5, which should be a positive number because we're raising it to, since we have an even number on our numerator, that's going to be like -1 to the 4th, and then raised up to the 1/5 power, which just takes the 5th root. So this should be positive. So we would get basically a positive number from this term here. And I'm actually going to go ahead and make some room right down here. So we would get a positive number from our first term. We would get -1 minus 4 is a negative number from our second term. And then -1 here would give us -1 minus 4 is -5 times -1 times 4/5. And then we would get 2 plus all that. So that would be -4. 2 minus 4 would be -2. So we'd get a negative in our third term. So a negative times a negative times a positive would give us a negative number. So since we got a negative number by plugging in -1, that tells us that our function is decreasing. Our slope is negative for this interval of all x values less than 0. Okay. Then we would do the exact same thing for plugging in 1, figure out if this whole thing is positive or negative. And I'm not going to show you that entire process. We'll just kind of skip ahead, and I'll show you what you would end up getting from doing that. And I had that written down somewhere, and oh, here it is. Okay, so if we did that, what we would find is that sorry, just checking here. Okay, so if we did that, what we would find is we would get a positive number by plugging in 1. Plugging in 1 into our derivative would give us a positive number as an output. So that tells us that our slope would be increasing. Our slope is positive. Or I'm sorry, our function is increasing. Our slope of our function is positive. And then we would plug in x equals 2 into our derivative. We would get a negative number telling us that our function is decreasing or that our slope is negative. And then when we plug in x equals 5, we would get a positive number telling us that our function is increasing because our slope is positive. So once you've kind of graphed out which intervals your function is increasing and decreasing, you can use the first derivative test. Tells us whether they're going to be maximums or minimums. So if we're decreasing to the left and then increasing to the right, our function is going to look like this at that point, telling us that x equals 0 is a minimum. And then if we're increasing to the left and decreasing to the right, that creates something more like this. So that tells us that our function is at a maximum at that point. So x equals 8/7 is a max. And then same thing again over here. We're decreasing and then increasing, creating a minimum at x equals 4. If you were decreasing to the left and decreasing to the right, that would create something like this. That is not going to be a maximum or a minimum. Or if you're increasing to the left and then increasing to the right like that, again, it's not going to be a max or a min. In this case, we did have a maximum or a minimum for all three of these critical numbers. So that's going to be it for that problem. So let's go ahead and go on over to the next one here. All right, doesn't look like there's any questions posted in the chat. Like I said, if you have any questions, feel free to throw them in the chat. I'll do my best to answer whatever questions you have, whether they're on topic or not. Of course, if you got on topic questions about the problem I'm doing, perfect, go ahead, throw them in there. But if you got some other questions, maybe a homework problem you're trying to work on or something, go ahead and throw them in the comments, and I'll do my best to answer whatever questions everybody has. All right. So now let's take this on a little bit further, and we'll talk about inflection points. So inflection points, basically how I'm going to demonstrate this, we're going to do this problem right here. We're going to find the inflection points and intervals of concavity of this function right here. So intervals of concavity and inflection points are extremely similar to finding critical numbers and intervals of increasing and decreasing, just like we did in the last problem, except what you want to keep in mind is that inflection points and concavity, those have to do with the second derivative. The second derivative of a function is going to tell you about those things, where the first derivative tells you about the slope and the intervals of increasing and decreasing. So rather than worrying about our first derivative, of course, we are going to need to find our first derivative in order to get to the second derivative. But rather than doing everything with our first derivative, we're going to be working more with our second derivative. So the first step in really any of these types of problems that have to do with finding inflection points is going to be to find our second derivative. So to do that, again, we're going to need to use the product rule in this case. So what we can do is we can say f is going to be this x piece here. G is going to be the square root of x plus 3 piece here. But instead of writing it as the square root of x plus 3, what I'm going to suggest is writing it as x plus 3 to the 1/2 power, because raising anything to the 1/2 is the same as taking the square root of it. So this is equivalent to the square root of x plus 3. But the reason why we want to do that is when we're then finding its derivative, when we're finding this g prime here, it's going to be much easier because we can use the power rule. So the power rule combined with the chain rule will tell us how to find this derivative. So chain rule says, and we need to do chain rule because we have this inside function here and then this outside function basically acting on that. So chain rule says that we're going to take the derivative of the outside, which is this 1/2 power piece, which we're going to be able to do using the power rule. So we'll bring the power down in front. Chain rule says to leave our inside function the same. And then we're going to lower our power by 1. So 1/2 minus 1 is minus 1/2. Because again, you'd have to do minus 2/2, which is negative 1/2. Okay, and then our f prime, we just need to find the derivative of x. The derivative of x is just 1. So now product rule says that we can cross multiply these. X times this here is going to give us x. Actually, let's go ahead and write this in a little bit neater format here. We'll say 1/2 times x plus 3 to the negative 1/2, and then 1 times x plus 3 to the 1/2 plus x plus 3 to the 1/2. 1 times it isn't going to change it, so we don't have to write that out. Then, like I said, we need to find the second derivative. So now we need to find the derivative of this here. The second derivative is always just going to be the derivative of the derivative. So there's two different ways we could go about solving this. We could do kind of like what we did in the last problem, where we could factor out this x plus 3 to the negative 1/2, or we can kind of carry on taking the derivative of each of these pieces separately. I'm not really sure which one would be easier. They'd probably be pretty similar. So we'll go ahead and just do each one separately. So we'll create kind of a separate little problem over here. So first of all, to take the derivative of this term here is going to be very similar to what we did to find the derivative of this function. We're going to have to do product rule. So we'll go ahead and say f is going to be our 1/2 x piece. G is going to be this other piece here, the x plus 3 to the negative 1/2. Then we need to find f prime, which the derivative of 1/2 times x is just 1/2. The derivative of x plus 3 to the negative 1/2, we're going to be able to just do power rule and chain rule, just like we did here. So we bring the 1/2 down in front. I'm sorry, bring the negative 1/2 down in front. Leave the inside function the same. Lower our power by 1. So negative 1/2 minus 1, or minus 2/2, would be negative 3/2. So our new power is going to be negative 3/2. And then by chain rule, we multiply this by the derivative of the inside. The derivative of x plus 3 is just 1. So we don't really have to worry about that. And then product rule says, again, we're going to cross multiply these. So 1/2 x times negative 1/2 x plus 3 to the negative 3/2. Those 1/2 are going to form a negative 1/4. Then we have an x, and then x plus 3 to the negative 3/2. And it is looking like I might run out of room here. So let me see if I can move this real quick. All right, perfect. Okay, and then we need to do this 1/2 times x plus 3 to the negative 1/2. Let me get rid of that there. It's a little confusing. All right. So then plus 1/2 times x plus 3 to the negative 1/2. All right, and then we still need to find the derivative of this piece here. So we haven't done that one yet. So to do that, x plus 3 to the 1/2. Well, we've already taken that derivative of that over here. That was a part of our previous derivative product rule piece. So we already know the derivative of x plus 3 to the 1/2 is 1/2 times x plus 3 to the negative 1/2. Okay, so now this is our second derivative. It's kind of complex, but we're going to be able to do something similar to what we did in the last one where we kind of factor some stuff out. So again, to find inflection points, we did our first step, which is finding the second derivative. Now that we have our second derivative, since this is such a similar process to finding the critical numbers where we took the derivative and set it to 0, same idea here. We're going to take our second derivative and set it to 0. So again, we have these three terms here. Again, we have a similar situation where it's easier to factor this out because then we're going to be able to create three kind of smaller, simpler problems out of that. So to factor this out, what we want to do is see what do these three terms have in common. Well, they both have a 1/2 that we can pull out. So we'll start there. And then they also both have, or all three of them have this x plus 3 to the negative 1/2 power. So we can also factor that out. And then we want to think about what's going to be left. So if we pull out 1/2, we're still going to be left with a negative 1/2 to get us to negative 1/4. We still have this x here. And then keep in mind, this is x plus 3 to the negative 3/2, where we pulled out x plus 3 to the negative 1/2. So again, what power would we need to make our x plus 3 raised to so that the power of this plus our negative 1/2 power out here adds up to negative 3/2? Well, it would just be negative 1. Okay, and then what are we going to be left with in this middle term here? So we pulled out 1/2 x plus 3 to the negative 1/2. That's exactly what this was. But you do want to be careful. This isn't just going to disappear. Whenever you're factoring out something like this and you factor out the entire term, it doesn't just disappear. You need to put a +1 as like a placeholder there, basically, so that when you, because if you imagine distributing this back in, we need this term to actually be there when we do that. Okay, and then again, we factored out a 1/2. Our 1/2 is going to be pulled out, and then we have again this x plus 3 to the negative 1/2. So that could have kind of been simplified by just combining these two terms into the same thing. Either way, we're going to end up with the same thing there. It's going to end up simplifying down the same. Because what we can do is instead of saying +1 + 1, that is just going to become +2. If I can get this to work, there we go. +2. All right. So now when we're trying to set this whole thing equal to 0, kind of like we did last time, what we can do is create these kind of two simpler problems. So we'll just take each of these factors and set each of them separately equal to 0 and solve those. So we will get 1/2 times x plus 3 to the negative 1/2 equals 0, and negative 1/2 x times x plus 3 to the negative 1 plus 2 equals 0. So this over here, if we multiply both sides by 2, that'll cancel there. 2 times 0 is still 0. So that's not really going to contribute anything there. Then to get rid of the negative 1/2 power, what we can do is raise both sides of our equation to the negative 2 power. Negative 1/2 raised up to the negative 2 is going to cancel out. So we're just going to have x plus 3 equals 0. subtracting 3 over gives us x equals 3. Okay, and then, actually, wait a second. Minus 3. There we go. Okay, and then over here, we're going to minus 2 to the other side. So negative 1/2 x times x plus 3 to the negative 1 equals minus 2. Multiplying both sides by minus 2 to cancel that there. Gives us x times x minus 3 to the negative 1 equals 4. So this looks a little weird, but what we can do here is, instead of thinking of x plus 3 to the negative 1, think of it as x times 1 over x plus 3. Because anything to the negative power like this, you can get rid of the negative power by moving that whole thing down to the denominator like this. Okay, so since it's x plus 3 to the negative 1, that'd be the same as 1 over x plus 3 to the 1. Well, x plus 3 to the 1 is just x plus 3. So we can rewrite it like that. And now, to simplify this, we can multiply this, as, think of it as multiplying fractions. You just multiply straight across. So what that's just going to end up with is x times 1, which is x, over 1 times x plus 3, which is just going to simplify us down to x over x plus 3. And that's equal to 4. Then we can multiply the x plus 3 over. So do be careful to put that in parentheses so that it'll cancel with that whole denominator, giving us x equals 4 times x plus 3, which then we can distribute that, giving us 4x plus 12 equals x minus x from both sides. 0 equals 3x plus 12 minus the 12. Divide by 3, giving us negative 4 equals x. Okay, so we got 2 inflection points here, but we do need to be very careful of something here. Notice our 2 inflection points are x equals negative 3 and x equals negative 4. But there's a problem with both of those numbers. Because if we go all the way back up to our original function here, our original function is a of x equals x times the square root of x plus 3. Think about what is going to, or basically what's going on with this function. Think about the domain of this function, I should say. You want to keep in mind that whenever you have a function with an even root, in this case we have a square root, you want to be careful that you cannot take the square root of a negative number. So basically what that means is any x value that makes what's inside the square root here negative is not a part of the domain. We can't actually plug that in. So when we're looking at this function, we need to remember that basically x plus 3, what's in the square root there, has to be greater than or equal to 0. So basically x has to be greater than or equal to negative 3, which means this first inflection point we got of x equals negative 3, it's not really an inflection point in the sense that this is a spot where our function is going to switch from being concave down to concave up, or vice versa, because it's really just the edge of the function's domain. Our function is not even defined for x equals negative 4, so that definitely is not a valid inflection point, because it's not even in the domain of the function. So you want to be careful when you find the inflection points to throw out anything you get that's not within the function's domain. Since this is basically right on the edge of the function's domain, any x values less than negative 3 are not defined. They do not exist. In terms of this function, this isn't really like a point that we want to think about putting on our number line and figuring out anything to the left and right. I mean, we can, but basically all that does is it tells us that everything to the left of x equals negative 3, it doesn't even exist. And since we figured out that this is the only place where our second derivative equals 0, we know that there's not going to be any other place to the right of -3 when we're doing our test to figure out where our function switches from concave up to concave down. There's not any points where x is greater than -3 where it's going to switch, because there's not any other points where our second derivative equals 0. So what that tells us is our entire function basically is going to be either concave up or concave down. Well, to figure that out, we could just do kind of the same kind of thing we did with our first derivative test, where we were trying to figure out where it's increasing and decreasing. We could just take any x value that's within this interval of -3 to infinity, so let's just say 0, and plug that into our second derivative. I'm sorry, not into our function, but into our second derivative. And if we plugged x equals 0 into this function here, what you would find is that that would give you a positive number, which means that our entire function is concave up. So it's curving up like that. It's like a smiley face kind of. So basically our entire function is going to be concave up all the way through. All right. So that's about it for that problem. Not seeing any questions in the chat so far. If you do have any questions, feel free to drop them in there, and I'll do my best to answer whatever you got. All right. Let's go on to the third problem here. So this one's a bit longer in terms of what it's asking us to find, but the function is quite a bit simpler than either of the other ones that we've dealt with so far. So it shouldn't be too bad. We're going to kind of put all this together and get into some curve sketching. So we're going to find the local max and min values of this function. We're going to find intervals of increasing and decreasing, and intervals of concavity and inflection points. So we're basically putting together kind of all the stuff that we've been talking about so far. And we're going to use all this information to sketch a graph of what this curve looks like. So let's go ahead and, we're going to start pretty much just by taking the derivative. That's going to generally be how all these problems start, where we're asked to find the intervals of increasing, decreasing, the critical numbers, the inflection points, all that kind of stuff. So first of all, we just need to find the derivative of our function here. So the derivative of this function, we can just kind of take it term by term here. Derivative of 2 is 0, so that's not going to do anything. Derivative of 3x is going to be 3. And then the derivative of -x cubed, we can find using the power rule. So we're going to again have negative, bring our 3 down in front, leave our x as x, and then lower our power by 1. So it's going to be -3x squared. So this is our derivative. So if we want to then find our critical numbers, we would take our derivative and set it equal to 0. And solve for x. So solving this for x, we can add 3x squared over to the other side, divide both sides by 3, and then take the square root of both sides to cancel out the squared. So that gives us x equals, and this is one thing you want to be careful of. When you take the square root of both sides of an equation like this, you need to take the positive and negative square root. So we actually have two different critical numbers here. X equals positive and negative square root of 1, which is just positive and negative 1. So in other words, we have x equals 1 and x equals -1 as our critical numbers. So now we can do the first or second derivative tests. And again, those are on my study guide if you want to go grab those. But I prefer the first derivative test. I think it's a little bit easier just because it requires finding one less derivative. But in this case, we're going to have to find information about inflection points and concavity. So we're going to need to find that eventually anyway. So if you wanted to do the second derivative test, this would be a good chance to try that out. But again, first derivative test, we're just going to draw our number line, put our critical numbers on there, and plug in some number that's in each of these 3 intervals. We split our number line up into 3 parts basically by having these 2 critical numbers here. So we'll plug in, let's say, -2, 0, and +2. So if we plug in -2 into our derivative, so into this right here, we're going to get 3 minus 3 times -2 squared is 4, +4. So that gives us 3 minus 12, so -9. So our derivative is negative when x is -2. So that tells us that our slope is negative and that our function is decreasing over here. Okay. Then if we plug in x equals 0, we're going to get 3 minus 0, which is 3, which is a positive number. So that tells us that our slope is positive, which means that our function is increasing in this interval. And then if we plug in 2 into our derivative here, we're going to get 2 squared, which is 4, times -3 would be -12. So 3 minus 12 again, which is again -9. So our derivative is negative, which means that the slope of our original function is negative, which means that our function is decreasing over here. So we can see that we have a critical number, or a critical point basically, at x equals -1 and at x equals 1. And that x equals -1 is going to be a minimum because we're decreasing to the left, increasing to the right. X equals +1 is going to be a maximum because we're increasing to the left and decreasing to the right. Okay, so now what we need to figure out is exactly where our inflection points are, because what that is going to be able to tell us is our intervals of concavity. So basically what we're going to be able to figure out is exactly when this function switches from concave up to concave down, somewhere between -1 and 1, presumably, but we can figure out exactly where that is. So to find our inflection points, we're going to take our second derivative and set that equal to 0. So if our first derivative is here, f prime equals 3 minus 3x squared, our second derivative is going to be f double prime of x, which is the derivative of our derivative. So the derivative of this here, derivative of 3 is 0. And then the derivative of -3x squared, again, is just going to be power rule. So we can bring our 2 down in front. -3 times 2 is -6. Keep our x as x, and then lower our power by 1. 2 minus 1 is 1. So it's just -6x. So then again, to find our inflection points, it's just like finding our critical numbers, but we do it with our second derivative instead of our first derivative. So we're going to take our second derivative of -6x and set it equal to 0. Well, it looks like there's just going to be one inflection point here. If we divide both sides by -6, we're going to get x equals 0. So we have one single inflection point at x equals 0. So what that tells us is our function is going to either switch from concave up to concave down, or vice versa at x equals 0. Well, to figure out which it is, we can do the same kind of thing that we did up here with our first derivative test. We can basically draw a number line, put our single inflection point on that number line. Now, do keep in mind, a lot of people do make this mistake of specifically putting 0 on this number line all the time. You only want to put 0 on your number line if it is your inflection point when you're testing intervals of concavity, or if it is a critical number when you're testing intervals of increasing and decreasing. Notice up here, 0 was not a critical number, and so we did not put it on our number line. It was in between 2 of the numbers that we had on our number line, so we did plug it into our derivative, but we did not put 0 on the number line. Just be careful of that you're just putting your inflection points or critical numbers on your number line. So now to figure out if our function is concave up or concave down on each of these intervals from 0 to -infinity and then 0 to +infinity, what we would do is just take some number within this interval. So let's just say -1 and +1 and plug that into our second derivative. So if we plug -1 into our second derivative here, we're going to get -6 times -1, which is +6. So a positive number in the second derivative tells us that our function is concave up here. Remember, our second derivative always tells us about concavity, where our first derivative always tells us about slope of our original function. Okay. And then if we plug in x equals 1 here, we're going to get -6 times 1 times +1, which is -6, which is a negative number. So that means our function is concave down here. So basically our function, it's going to be decreasing from -∞ to -1, increasing from -1 to 1, decreasing from 1 to infinity, and the point where it switches from curving upward to curving downward is right at x equals 0. So if we now want to kind of sketch a graph of this function, we could kind of combine the information we gathered about our slope plus the information we gathered about our concavity, and we know that our function is going to be something, well, let's just worry about the horizontal axis for now. Something like this, where we have a minimum at x equals -1. It's going to be concave up until we get to x equals 0. And then right at x equals 0, so right above here, it's going to stop curving upward and start curving back down. And then we're going to have our maximum, our local max at x equals 1, and then it's going to keep coming back down here. So what we could figure out if we wanted to is also exactly where these points, these max and min values are. If we wanted to do that, all we would have to do is take x equals -1 and x equals 1 and plug them back into our original function. So if we figured out f of -1, that would just be plugging in -1 in for x here. So we would get -1 cubed. Well, let's just write out how we would do that here. So -1 cubed is -1, but there's a negative here, so we're actually going to get +1 there. 3 times -1 is -3, and then 2. So 2 minus 3 is -1, +1 is 0. So at x equals -1, we're right on the x-axis actually. So in reality, our x-axis would be right here, going through this point here. And then our y-axis would come up here like this. Here's x equals -1. Here's x equals 1. We could figure out exactly how high this point is by simply plugging in x equals 1 into our function. So instead of -1 here, we would do f of 1, which would be 2 plus 3 times 1 minus 1 cubed, which would just be 2 plus 3 is 5, minus 1 is 4. So this maximum here would occur at y equals 4. And now this gives us a pretty good idea, or a pretty good sketch of what our function f of x is going to look like, something like that. All right, well, that's about it for that problem. I don't see any questions in the chat, so we'll go ahead and wrap things up there. Hope you all found this helpful. If you did, please be sure to hit that like button on your way out. It really helps spread this around and get more people in these videos so we can get more questions and help more people learn all this stuff. Really appreciate it. And be sure to subscribe and hit that bell icon down there so you're notified of all my new videos. I'm doing a live stream every Monday night at 5 Pacific, so hope to see you back next week. Thanks, and see you then.